We saw this problem before, this parameterization, and we saw how they traced out, going around here, coming to a stop, speeding up, really going fast back to here. So we want to learn something about the velocity of a point tracing out on the parameterized curve as t goes through its range of values, in this case from 0 to 4. And here is the animation of that again. Notice how it starts off fast, comes to a stop, goes backwards, back to the beginning. So again, watch it again. It's going to start off fast, slow down, come to a stop, turn around backwards, speed up, and go to the start. There it is. Okay? So speed sounds like a rate of change, which sounds like a derivative. So you can pretty much guess what's going to happen here. At a point x, y, or x of t, y of t, at a t value of t, here's where you are. Then as you move an increment of delta t to the next point, x of t plus delta t, y of t plus delta t, at the point, at the t moment of t plus delta t, then you have a change. And so we have, in a delta t increment of the parameter, we have the change in x values and the y values to be this change for the x's and this change for the y's. So the average rate of change of x at a t value is this difference quotient, looking just like the derivative, and similarly the average rate of change of y at a t value is this difference quotient here. Thus, when we have the delta t going to 0 in a limit, we get the instantaneous rate of change of x with respect to the parameter value of t, and we can call that dx dt. We can also call it x prime of t. You can interchange that. Also, we have dy dt equaling to that limit as delta t goes to 0, the instantaneous rate of change of y with respect to t, and we could also write that as y prime of t. Then we continue on. This v sub x is the x-coordinate of velocity vector, which we'll talk about in another video, and it's the dx dt, the velocity in the x direction, and v sub y is the velocity in the y direction. The speed of a point being traced out for a given t value is this formula here, y, see below. So here's why that is. Alright, so here's your curve that was the parameterization for which was given earlier in this video. When you're at a t value, but you're moving to a t plus delta t value, then you have a change in x. In this case it would have been negative, because as you go from one point to another, you're going backwards with your x, but you're going up with your y, so the delta y would have been positive. But anyway, you have a nice right triangle there. So the hypotenuse is the distance that you traveled during that delta t parameter change. So here is the distance traveled on the path, and you're doing that in a delta t time increment. So the speed of the point being traced out is approximately this ratio of the distance over the increment in the t parameter. Then you can do a little algebra, square the delta t and move it underneath the radical. That's fine. And then that leads to this formula as you divide delta t into both. And of course now when the limit as t goes to 0, we have our speed formula right here. And we can do an example of that. Find the speed of a point being traced out when the t value is 0.5. And this was the parameterization that we were working with. Okay, so this is the point we're talking about right here. So we already saw the video, the animation, that it took off fast, started to slow down, just came to a stop. So let's see what the speed is right at t equals 0.5. So we do our dx dt, get this, clean it up a little bit, evaluate it at 0.5, plug in 0.5 for t, and you get approximately this value, negative 2.95. dy dt, take the derivative, we're using the chain rule there, clean that up, evaluate it at 0.5, and it turns out you get this. So the speed of a point being traced out when the t parameter is equal to 0.5 comes out to be 3. And what that means is that at the moment when your t parameter is 0.5, the curve is being traced out at about 3 units on the xy graph per 1 unit of t parameter. What is the speed at t equal 1? Same thing, you get your derivatives, but now we're over here. So it should be a slower speed, because remember the animation took off fast, started slowing down to come to a stop at 2. So this should be less than 3. So you do your derivative, evaluate t equal 1, plug it in, and you get approximately negative 0.28 for dx dt, and for dy dt, plug in t equal 1, you get approximately negative 1.98, and when you put that into the speed formula, you get 2. Sure enough, that is a lesser number than 3. So it's a slower speed. So the trace is slowing down exactly the way the animation showed it was. Then we have, what is the speed of the trace when t equals 2? So on the animation, that's when the trace came to a stop and turned around and went backwards. Let's see that again. Alright, here's your animation again. Let's watch what happens when you get to t equal 2. It slows down, stops momentarily to go backwards. So let's see if the math verifies that. So evaluating the dx dt at t equal 2, you plug in 2 there and you get 0, and that zeroes this whole thing out to get 0 there. dy dt, plug in t equal 2, 2 plugs in right here, zeroes that out, you get 0, and sure enough the speed is 0 squared plus 0 squared is 0. So momentarily, when the parameter value is t equal 2, the trace has stopped in order to turn around and go backwards. And this is just a reminder note that in future videos we may interchange x prime of t and dx dt and y prime of t in place of dy dt.